Do you have claustrophobia, the fear of being trapped? Perhaps you went to a corn maze once and had a hard time getting out. As humans, the easiest way to solve a maze is by placing your hand on the right or left wall and following that wall until you've reached either the start or the end. But what if we weren't humans? What if we were a liquid that could be everywhere all at once? Well, take a deep breath because it's time to learn about your BFs. Breadth first search is an algorithm that iterates over a graph in waves. Think of it as if you were to pour water in a maze. How would it solve the puzzle? By moving one iteration forward to queue up more actions and then repeating, breadth first searches have a wide array of uses in computer science. This algorithm, however, is much stronger than simply solving mazes. What if I told you that this is what connects everyone in the world? Take for instance this visual. Let's say I'm here and you're over here, and between us are all of our friends and our friends' friends. I know Bob, and Bob knows Chip and Dale knows Ren, and Ren knows Tom and Jerry knows Charlie, Snoopy, and Sally, and Snoopy knows you. That means because of Snoopy knowing Jerry, knowing Ren, knowing Dale, knowing Bob, you know me. In social networking, this is called 6 degrees of separation, and is the idea that we're all connected by 6 of our friends. Furthermore, this connection can be found by doing searches such as breadth first search, as it scans over all of our friends to see who they know and so on. With the visual of this algorithm in place, let's take a look at how we can implement it. A really common practice that you'll see done is having a pointer referencing a parent node of the search. In this example, start has 2 kids, east and south, and east has 2 kids, east again and south just has south. Finally, the farthest east goes south and we reach the end. That node then lights up and all of its parents light up and their parents light up until we've reached the start. While this is one way of doing it, it should be noted that depending on your language, doing this can be very demanding on the CPU. As with this case, Python was one of the languages that didn't appreciate the simplicity in pointers. So, instead of having pointers, what we can do is we can encode the board with a path to get back to the start, and keep all the same logic minus the classes. For those of you familiar with algorithms, you may be wondering, why don't we use a depth first search? While a powerful tool, depth first searches may not always yield the most optimal path to an end goal if there's multiple solutions, whereas a breadth first search will always give you the shortest path. This wave-like search concept is used in video games with the A-star algorithm and is what many enemies use to track down the player through a wall or maze. Alright, with all that out of the way, let's dive into the code. To start, we want to have our cardinal checks, which validate the next selected tile is a valid one and not a border, wall, or previous selected tile. After that, we create a list to act as a queue for all of our future moves. With that queue, we pop up one element at a time and store all of its valid moves into a new queue to be used once we depleted our active one. This is also the step where we have one child node reference their parent node, or, in our case, populate the board with a breadcrumb trail to get back. We then loop through until one of 2 conditions are complete. Either we've reached an empty queue of moves, or we found the end tile. If we depleted all the moves in the queue without finding the end tile, we know that there is no solution to this maze. If we find the end tile, then we want to take the tile which got us there and backtrack through the maze to populate a trail leading from the end to the start. And voila, you too now know how to do a breadth first search. If you want to play around with this for yourself, my website can be found in the comments and descriptions below. The code is posted publicly to my GitHub for a more in-depth look into the project. If you enjoyed this video, please consider giving it a like and subscribe. Till next time, y'all.